Our linked list is getting better and better. Now let's take it to the next level. Let's add a new method for getting the size of this linked list. So public int size. How are we going to calculate this? Well, one approach is to traverse the list. So we start from the beginning, go all the way to the end. Every time we get a node, we increment a counter variable, and then we'll return it. The problem with this approach is that every time we call the size method, we have to recalculate the size. This is not efficient. What if our linked list has 1,000,000 items? We don't want to traverse such a big list every time we call the size method. There must be a better way. Well, we can declare a private field in this class. Let's call it count or size. And every time we add or remove an item, we'll update that field. Then in the size method, we'll simply return the value of that field. So let's go ahead and implement this. Over here, where we have declared our private fields, I'm going to add another private field, call it size. Now, in our add last method, after we add a new item, we're going to increment size by 1. Similarly, in our add first method, we need to write this code, size plus plus. And in remove first, we need to decrement it by 1. And one last time in this other method. That was very easy. Now, in our size method, we'll simply return the size field. Let's test this. So I'm going to go to the main method. Initially, after we create the list, let's print the size and make sure it's 0. So print list.size. Now we add one item. Let's print the size one more time. Then we add 2 more items. Let's print the size. Now let's run the program and see what we get. So initially the size is 0, beautiful. Then we get 1 and 3, exactly what we expected. Now what if we use the add first method? We should see the exact same result. There you go. What if we remove one of these items? So I'm going to call list.remove last and then list.remove first. And after this, I'm going to print the size of the list. So we should get 1. There you go. So after removing 2 items, whether from the beginning or from the end, the size comes down to 1. So here's what you need to take away. As you're implementing operations in your data structures, you need to think about efficiency. With this new implementation, the runtime complexity of this operation is O of 1. With the other solution that involved traversing the list, the runtime complexity would end up being O of n. Next, we're going to look at converting this list into an array. Actually, I realized I made a mistake here. In the remove last method, we are decrementing the size field at the end. But here we have this if statement, and if this condition is true, we are jumping out of this method. So if our list has a single item, the size is not going to be decremented by 1. There are 2 ways to fix this problem. We can come over here and set size to 0, or we can remove this as well as the return statement, as well as these ugly curly braces. Here we add an else clause, then move this logic inside the else block, and finally decrement size by 1. We could also do this before changing the nodes, but I think this logic is a bit weird. It makes more sense to remove the node and then decrement the size. So I'm going to move this down. I think that's better. Now we have the same problem in the remove first method, but I leave it up to you to fix that problem.